Hello everyone, welcome back to the course. This week we'll try to delve a bit deeper into the current market for hydrogen, and if a market for hydrogen exists today, how the hydrogen is getting produced. So let's first try to understand, do we have a current market for hydrogen? Are we using any hydrogen currently? Of course, we don't really see any cars or buses or trucks running on hydrogen. Of course, we see that on television or popular literature, but not into our day-to-day lives. So where would the hydrogen be getting consumed today? So if you look at the statistics and the current demand for hydrogen, you would see that in the year 2020 and in the year 2025, we had a significant demand for hydrogen, roughly of the span of 100 million tons. Now 100 million tons seems to be a good number. If I am producing some chemical of the tune of 100 million ton, it must be having a great demand. And this happens to be true for hydrogen as well. Hydrogen as such is a chemical that is produced a lot globally. If I talk about India, the current Indian production roughly is around 6.5 to 7 million tons. Okay, so if this is the quantum of hydrogen that is produced every single year, maybe in India or globally, where exactly I am using it? So if I try to understand where exactly I am using the hydrogen, you would see that a majority of the hydrogen goes in the refining sector, which basically is associated with the crude refining. The crude that we are digging from the earth's crust and then making different kinds of fuels like diesel or petrol is a big consumer of hydrogen. Then another major consumer would be the industry. So if I talk about the industry, which type of industry am I talking about? I am basically talking about the ammonia industry, the methanol industry and the iron and steel industry. These are the three major industries which are consuming a lot of hydrogen, and this has been going in since many decades. So it's not something new. Hydrogen has been finding a great use in the refining and the industry sector. But why don't we see much of the hydrogen around? Because in all these industrial and refinery applications, it's locally produced and locally used. So normally you would not have hydrogen being produced at one place then transported to another place for getting used. So normally these industries or the refineries would have their localized units for production of hydrogen, where they produce the required hydrogen and this is used in the same place. Further, we also need to understand that most of these processes are occurring at high temperatures and pressures, and not to say that hydrogen and its derivatives like methanol and ammonia are hazardous and toxic. So there's a great deal of safety requirement for them, and this is also one of the reasons why these don't have much of access to the public in the past. But things might be changing in the future when the use of hydrogen becomes much more popular and it gains much more wider acceptance in the society. Further, if I talk about the future, you might see the application of hydrogen happening in the transportation sector, the power sector, ammonia as a fuel or synthetic fuels, buildings, and even like hydrogen getting injected into gas pipelines. But this is something that we can see happening in the near future. Further, we also need to understand that in majority of these applications, hydrogen is used along with a gas called carbon monoxide. So these two gases, hydrogen and carbon monoxide, are often used together, and the combination is known as synthesis gas. It also happens, as we'll be discussing in the future classes, that these two gases are also produced together. And so in the past, what has happened that the production and the utilization of these two gases have always been together, such that they have become known as a gas called synthesis gas. Now let's try to understand the application of hydrogen in different sectors one by one. Let us start with the application or the utilization of hydrogen in the refining sector. So when I talk about oil refineries, we know that we are talking about a fractional distillation column, and the input to the fractional distillation column would be some kind of crude, and then this gives us different kinds of end products. The major end products that we might be aware of would be fuels like petrol, which is also known as gasoline, diesel. We might be talking about different kinds of gas. A typical gas that we use in our homes is LPG, liquefied petroleum gas, which is nothing but a mixture of propane and butane. And then there could be different grades of fuel oils as well. So this is what a typical refinery is doing, and not to say that like every refinery that is functioning has different kinds of operations depending upon the place, the demand for the products and the crude that it is taking in. But not to say like for all the refineries which is trying to produce majority of diesel and gasoline, we see that these two fuels, diesel and gasoline, tend to have a higher hydrogen to carbon ratio. If I talk about diesel, the hydrogen to carbon ratio is roughly of the order of 2, and this happens to be somewhat on the lower side, around 1.8 for gasoline, which we also know as petrol. But if we talk about crude as such, the crude tends to have a hydrogen to carbon ratio which is on a lower front, which is roughly of the order of 1.4 to 1.6. Now, if I would have to increase the hydrogen to carbon ratio of a fuel, how can I do that? Now, there are three ways. I can either add in hydrogen or remove carbon in the form of carbon itself or as carbon dioxide. Now, different refineries would be functioning in slightly different ways, and they might adopt one or different ways for achieving this purpose. But the most beneficial way would be to add hydrogen, because if you are losing in carbon, inevitably you are also losing energy, because carbon also seems to be a big energy provider for any of the application of these fuels. So, the best way of achieving this means would be for the addition of hydrogen. Now, if I talk about this addition of hydrogen, this has been going on since many decades. But what we also notice is that the use of hydrogen in the refineries has been increasing over the past few years. Now, why would the need of hydrogen in the refineries increase? Of course, we know that like hydrogen would be needed to increase the hydrogen to carbon ratio of the fuels. That makes much more sense to us, like petrol or diesel. But why would the requirement increase over the time? Well, there are two factors that are behind this particular phenomena. One is the fuel quality or the fuel standards or the emission standards that are becoming stringent day by day. Currently, we are using the Bharat 6 standards, and if you go a couple of years back, maybe 5 years back or 6 years back, the prevalent standard at that time was Bharat 4, before that Bharat 3. And as we are increasing the standard so as to meet the emission norms, the quality of fuel also needs to be upgraded. So, if you are looking for a better quality fuel with lesser amount of sulfur and other compounds, naturally we would have to add in more hydrogen for processes like hydrotreating, which remove sulfur. Another phenomena that has been observed is that normally the crude that we are importing with as time progresses is becoming from the heavier end of the crude oil spectrum. The lighter spectrum, which was on the top, has already been utilized, and the crude that we are extracting now is more on the heavier end. The result is that we would need even more hydrogen to process this kind of crude and to come up with meaningful results or meaningful fuels which we could use in our vehicles. So, let me repeat, what has been happening in the past few years is that the fuel conditions or the fuel emission standards have been becoming more and more stringent. So, we need cleaner fuel entering our vehicles. And what has also been happening on the input front is the crude that we are now generating or extracting is coming from the heavier fraction, which needs even more refinement as compared to the earlier cases. Now, let us try to have a look at a typical refinery. Of course, let me repeat that all refineries are different in one aspect or the other, but this is what a typical refinery is going to look like. There could be modifications in the diagrams that you can come across from other literature. But just to make you understand where exactly I am using hydrogen in these operations, we have this small diagram in front of you. So, what is entering is crude. So, this crude, after removal of maybe water and a few salts, enter into the atmosphere distillation column, and on the top you would have the light gas escaping, and through the gas plant you would have the propane and other lighter gases, basically giving you gases like LPG. This gas plant also produces butane and alkylates, which could be used for conditioning of the gasoline. Then further, if I talk about the middle products, it basically includes the different grades of naphtha, which leads to the production of gasoline, plus the distillate that leads to the production of diesel. The heavier fractions basically go to vacuum distillation, and they might end up being used as fuel oil or other uses in the form of asphalt. Now, where do you exactly require hydrogen are these processes which are called isomerization, hydrotreating, which almost goes in all of the products that you find below naphtha, and there is also a process called hydrocracking. So, these are the three main areas where you would be requiring hydrogen. Plus, a refinery also happens to be a good producer of hydrogen. It's not that I'm only using hydrogen, I also tend to produce a good amount of hydrogen in a refinery, and that is primarily happening because of the naphtha reformer. So let us primarily try to understand like what all would be the aspects, and before that I also like to give you the spectrum of at which these kind of products would be released. So I am talking about the boiling points in here. So if I am talking about the boiling points varying from 30 degrees Celsius to 196 degrees Celsius, I will be getting gasoline grade fuel. If I am looking from 196 to 235 degrees Celsius, it is basically kerosene and jet fuel. Above 235 going all the way to 360 degrees Celsius is the diesel, and beyond 360 degrees Celsius boiling point I am going to get fuel oil. So let us try to briefly understand like these operations which require hydrogen in a refinery. So here is a video which I have adopted from YouTube. The link is there for your reference, which you might want to see. So this is a typical refinery, how it looks like. So this is the distillation column, which is basically separating the different aspects in terms of gasoline, naphtha, kerosene, diesel and heavy oils which might be coming in. So they are just separated on the basis of the boiling point that we have. But as you would see, that has a lot of processes, and one such process is called hydrocracking. So what happens in hydrocracking is that we have many heavy oils or heavy naphtha which are long molecules. So if I am talking about heavy naphtha, I am basically using catalyst and hydrogen for breaking these bigger molecules into smaller molecules, which could lead to the production or increase in the production of petrol or diesel, which are the primary products of a refinery. So what I am doing in here is breaking bigger molecules into smaller molecules. Then another process that is important to understand is the hydroreforming. Another process that is important is hydrotreating. So when I say hydrotreating, I am basically aiming to reduce or remove these sulfur compounds from gasoline, which is the major product. So the gasoline that we produce has sulfur impurities, and I could have the addition of hydrogen, which basically makes the sulfur escape as H2S gas, and this tends to consume somewhat of an hydrogen as well. And the side products are basically used as fertilizers or other ingredients for the pharmaceutical industry. The major aim of these things are of course to increase the octane number of the fuel. So let us again try to understand this one by one. So the very first process in the refinery that is going to use hydrogen is going to be the naphtha isomerization process. So when I say isomerization, I am basically producing isomers in the naphtha range fuel. So we all understand what I mean by isomers. It's the compounds having the same molecular formula but different structure. So basically what I am doing is converting linear chain molecules into branch chain molecules. The aim again here is to increase the octane number. And how does the process happen? So you have the light and naphtha entering. After a dryer, you would want to heat this naphtha, add in hydrogen, so that's to convert these linear chain molecules into branch chain molecules. It happens at roughly 200 degrees Celsius, and in the presence of catalyst it works best, and what you will be producing is the isomerate at the end. Of course, I'm telling you these things because I just want to explain you the need of hydrogen in the refineries. It's in no way you would be required to cram or memorize these processes in detail. And if I talk about the consumption of hydrogen in a process like this would be of the order of 40 standard cubic feet, which is basically the volume per barrel of feed. So when I am talking about a standard cubic feet per barrel, this is a standard unit that is used for in the refinery processes. But again, like why do I am so interested in increasing the octane number of the fuel? Because the isomerization process as well as the hydrocracking is basically aimed at like mainly working towards the octane number of the fuel. Let us first try to understand that. So for this we need to understand the basic difference between a petrol engine and a diesel engine. So when I talk about a petrol engine, it again we would have something called a spark plug that causes the spark for the combustion of the fuel to happen. Now this is something that happens to be absent in a diesel engine. What happens in a diesel engine is that the combustion happens because of the compression. So if you would have to see the difference between the two, so we have the functioning of a petrol engine here, where in the compression stroke, so when the compression is happening, the combustion is basically made by the spark that is happening in here, and then we have the release of the exhaust gases. Now compare this with a diesel engine, there is no spark plug present here. The ignition happens in the compression when the fuel is released, and the fuel gets spontaneously combusted because of compression. And further, we also understand that both of them are dealing with different kinds of fuels. So diesel happens to be dealing with much bigger molecules as compared to petrol. Now what happens in a petrol engine when the combustion is happening because of compression even before the spark plug? So what do we mean by knocking? So knocking, as we have discussed, means like the combustion happens because of compression before the spark plug gets in. So this is a normal IC engine that you can see, and what you see is the combustion was initiated in the compression state just before the spark plug could plug in. So you can see the combustion happening here, and that's not good for the efficiency and the life of the engine, and that is why we would need a lot of pretreatment so that these kind of phenomena doesn't occur in reality, and this phenomenon is also called knocking. So what happens when the combustion happens in a petrol engine just because of compression even before the spark plug gets in, and this is what is called knocking. And to avoid this knocking phenomena, normally we would be using a high octane fuel so that it increases the engine health and also is good for the efficiency of the engine. Now another place where you would be normally using hydrogen would be the hydrotreating of naphtha as well as the distillate. Now the aim of the hydrotreatment process is basically to remove sulfur from the streams. So why would you need to remove sulfur? Because sulfur, whenever it's combusted, is going to compose different grades of sulfur oxides, and when this is emitted through the tailpipes, it will go into the atmosphere, react with water, create weak acids, and lead to a phenomena in a long run which is called as acid rains. And this is why there have been a lot of problems with respect to the sulfur that has been released in the atmosphere in the recent past. So the restrictions have been there on the amount of sulfur that goes into the fuel, and normally this process is also called as the hydrodesulfurization unit. But nonetheless, it would use hydrogen which would react with sulfur to create the H2S gas. The other advantages of this process, one major advantage is not only sulfur is get removed, it also removes some amount of nitrogen from the fuel, which happens to be a beneficial way. Further, the removal of unsaturated molecules like olefins and diolefins also gets removed, and it also helps in the removal of polynuclear aromatics, which are also called as the PNAs, which helps in increasing the cetane number for diesel. Another added advantage of this hydrotreating process is this tends to decrease the density of the fuel. Now, as many of you would have noticed that whenever you are going to the petrol pump, you are paying per liter of the fuel rather than per kg of the fuel. So, if I am leading to a decrease in density of the fuel, possibly I am increasing the volume for the same weight of the fuel, and this is also the advantage of the hydrotreating process. If I would want to explain you a typical hydrotreating process, so the major feedstock is the gas oil, which needs to be heated before entering the reactor, and this reaction is normally occurring at around 320 degrees Celsius with the help of a catalyst, and the catalyst is normally cobalt molybdenum on a aluminium support, and you would have the hydrogen entering in here. The sulfur gets separated in this reactor, which needs to be removed through different grades of separators, and finally you would have another distillation column downstream which will be removing either the naphtha or the diesel grades fuel. And further, if you can see, based upon the type of input fraction that I am entering the hydrotreating fraction, you would have the different requirements of hydrogen, but somewhat greater than the isomerization process. Also, we need to understand that because of technologies like this, the sulfur emissions have widely been controlled in the atmosphere. So, if we talk about the conditions of a few decades back, the problem of sulfur oxides leading to acid rains was a big problem in Europe and the developed frontier of the world. But because of the consistent policies that was adopted for the use of fossil fuels which are made to treat their sulfur components, it has led to this drastic reduction. So, you can see over the past 2 decades, the sulfur emissions in the US and the Europe have came down drastically. If you talk about Asia, we are also on the downward trend, and that is one of the reasons why you don't tend to hear about phenomena like acid rains much in the popular literature now, but this has been achieved in the recent past. Further, another place where you would be using hydrogen would be hydrocracking. So what happens in a hydrocracker is that we would want to break bigger molecules into smaller molecules, which could lead to an increased productions of fuels like diesel or gasoline grade fuels. If I talk about the operations, like this process occurs at slightly elevated temperatures of around 400 degree Celsius or plus. So you would again have the gas oils entering in, and the first reactor is very similar to the hydrotreater as we have discussed in the past slide. And then what happens is that we would have this hydrocracker, which is going to break the bigger molecules into smaller molecules, and then we would have again a distillation column which might want to separate the diesel and the naphtha grade fuels. Well, this is one place in a refinery that would have significant hydrogen requirement. So normal hydrogen requirement would be of the order of 1000 to 3000 standard cubic feet per barrel of feed. Now these are the three main places where you would be requiring hydrogen. What about the hydrogen production? Well, that happens in a place called the naphtha reformer. So when I talk about the naphtha reformer, I am basically trying to convert some of the aliphatic compounds, which are paraffins or cyclic compound like naphthenes, into aromatics like benzene, toluene and xylene. Again, the primary aim is to increase the octane number. Now suppose I would want to change the structure of a paraffin like this, which has a research octane number of 0, first to naphthene and then to aromatics like benzene. It would lead to significant production of hydrogen and also an increase in the octane number of the fuel. So these processes are basically undertaken to maintain a steady octane number for the fuel that the particular refinery is generating. And further, there could be different grades of fuels that are generated based upon the octane number. You might have heard about normal petrol and extra premium petrol. So the difference between those kinds of petrol is the octane number. And this process also tends to produce significant amount of hydrogen, which could be of the order of 500 to 1300 standard cubic feet per barrel. Now if I talk about the operation of this plant, so this has been explained to you, like we would have the naphtha coming in, which needs to be broken down into the different fuels. So the first thing is you would heat naphtha, and then you would have the different reactors occurring or acting in series, and the normal temperature is roughly of the order of 500 degrees Celsius or so. And then you would have a distillation again downstream for getting the different grades of fuel, and of course hydrogen goes out as a byproduct in this particular process. So if I would want to summarize the different types of hydrogen requirement over the past, here is a nice summary which is basically coming from the Oil and Natural Gas Journal, and in this case the reference is also given at the bottom of this slide. So this basically shows you the different areas where the hydrogen is getting consumed and where the hydrogen is getting produced. So here we have the typical range, and then I have just put in an average value for this. This is basically the amount of a particular crude fraction that goes into this particular unit, and then this basically gives the hydrogen production or consumption from that particular unit, and the data is given for the year 2008 and 2020. So let us first try to understand how things have been changing. So if I see the hydrogen consumption, you would see the hydrogen consumption is mainly happening in the hydrotreating and the hydrocracking over the years. And what we also see based upon the difference between 2008 and 2020 is that the hydrogen consumption has increased over the years. So if you see, the hydrogen consumption was roughly of the order of 22 million standard cubic feet per day. In 2008, this would have increased to 29,000 standard cubic feet per day in the year 2020. Note to say that the production for the reformers happens to stay in almost similar lines, and if we say the hydrogen production capacity, this has been added over the years, and so we see that in spite of the significant hydrogen that is getting produced because of the naphtha reformer, we still would have to have produced significant amount of hydrogen in a typical refinery, and that normally is made through a steam methane reformer, about which we will be discussing in the subsequent classes. But we need to understand that currently there is a significant need of hydrogen in the refineries. So if I talk about this number, the consumption that was happening in the year 2020, so this is roughly 29,529 standard cubic feet, which would basically turn out to be 23.6 million tons per year of hydrogen. And if I multiply this with the nominal rate of hydrogen, say being $3 a kg or $3,000 a ton, which I am assuming to be price of hydrogen, the delivered price of hydrogen, this would come out to be a whooping $69 billion, which is basically pointing out the huge requirement of hydrogen in the refineries. So just the requirement of hydrogen in the refineries can have a value of the tune of roughly $69 billion. Then another place that is very close to the refineries where you would have the application of hydrogen would be the petrochemicals. Now petrochemicals complexes are normally very close to the refineries because that is where the major feedstock is coming from. So again, when I say about petrochemicals, I am saying about the different kinds of products that we use day in and day out. If you look around yourself in the room that you might be sitting, there will be a lot of petrochemicals. The major grades of plastic that you're using are petrochemicals. The synthetic clothes that you would be using are petrochemicals. The different kinds of equipments, maybe mobile phones or laptops or the computers or the workstation through which you are watching this video, would have significant amount of petrochemicals forming the raw material, making you perform your day-to-day work. So as such, we use a lot of petrochemicals throughout our life, and the major feedstock again remains gas and oil. But in the petrochemical sector, what is happening is that both the products as well as the input material tends to have a hydrogen to carbon ratio of roughly around 2. So which means there is no significant requirement of addition of hydrogen from outside. But there are some processes that would be producing hydrogen, and there are going to be some processes that consume hydrogen. And let us try to understand these processes in detail. So when I am talking about petrochemicals, so again with the help of the small video you can see how much petrochemicals are there around us. So they of course start with the oil and gas industry, and these plastics or the wraps are petrochemicals. The plastics are petrochemicals. The fertilizers that we use are fertilizers. The clothing, the devices, the tires are coming from all petrochemicals, and this is expected to be a big driver for the global demand instead of the fuels that we will be using for different grades of transportation. Now when I talk about petrochemicals, it would have like different areas where the hydrogen is getting produced or hydrogen is getting used. So one process where hydrogen would get used would be the naphtha hydrotreating. Now as we have discussed in the earlier slides, so when I say hydrotreating, I am basically removing compounds like sulfur through the addition of hydrogen. And as the conditions are becoming more and more stringent for the use of the fuel, the requirement of this hydrogen is also becoming more wider. And this is one place where I would be using a lot of hydrogen basically to convert or to bring down the sulfur compounds, and it also helps like in the final distillation, which helps in removing the heavier components that would otherwise have caused problem and causing problem like coking. So that is also avoided with the help of hydrotreating, and it also becomes easy for processes like steam cracking. So if I talk about the petrochemical complexes, one of the major product is the production of different grades of polythenes. It could be low density polythene, high density polythene, or linear low density polythene, and these are produced mainly through a process called steam cracking. And it also so happens that whenever I am using steam cracking, hydrogen would be coming out as a side product. So it happens that like the hydrogen that comes out from the steam cracking is used in other processes like naphtha hydrotreat. Another area where I will be using hydrogen would be like in the downstream processes, specifically in the polymerization process. So whenever you are forming polymers leading to different grades of plastics, it basically needs a chain termination step wherein the use of hydrogen is important. Further, hydrogen also helps in removing the olefin groups. So when I say olefin, these are the dual bonds which might happen, and hydrogen helps in unnecessary creation of these olefin groups. And further, it also helps in the oxidation stability of the finer polymer that might be produced. But again, the consumption of hydrogen for this is not very significant. Another area where hydrogen would get produced would be the naphtha reforming. So this naphtha reforming, again we have slightly discussed in the previous slide. So what is happening in the naphtha reformer is we are converting the aliphatic molecules to aromatic molecules, and this produces significant amount of hydrogen, but this hydrogen again would get utilized in the complexes. And one of the major products of this naphtha reforming will be the compounds known as benzene, toluene and xylene. Now these three chemicals happen to be important compounds such that they form the precursor of many of the chemicals that we use in day-to-day lives. Just to give you an example, so you would have a diagram here where you see the whole range of end chemicals that you can get from these three chemicals, which are benzene, toluene and xylene. And if I look at the market projections, you can see that these three chemicals are going to grow rapidly in the coming few years. So if I consider from today till 4 years in the future, we can see that the consumption of these chemicals in the form of benzene, toluene and xylene might almost become double. So it is also proposed that in the future a lot of growth in terms of the petroleum products are going to be propelled by these kinds of compounds. Let us also briefly try to go through the application of these petrochemicals in the form of three chemicals. The first one is benzene. So I believe we all have heard about a chemical benzene, which is 6 molecule chain, and it happens to be a major precursor for cyclohexane. And if you remember your school days, again cyclohexane is one molecule which is used for the production of nylon 6 or nylon 6,6. Now these are the major polymers that you would be using. Further, benzene is also used for production of polystyrene. So what is polystyrene? You would have seen these kind of packaging material. It's basically a thermocol that we use for packaging of any electronic product, and again this is where polystyrene is used. Another major use is the creation of acrylonitrile butadiene styrene, which is a hard grade of plastic basically used for toys. If you have seen the Lego toys or something similar blocks which children play around with, this is nothing but the ABS which is being used. Another molecule is toluene. Toluene as such has no direct use, but it is used for the production of benzene. But an important thing about this benzene and toluene is that they might play a bigger role, as we will be discussing in the future classes, in the transportation of hydrogen over long distances. So this is something like this kind can form the organic hydrogen carrier, which can help in the transportation of hydrogen in the long run. Another major molecule is the xylenes, which are basically C8 aromatics, and they basically happens to be either ortho, para or meta form. So we don't have much of the application for the meta-xylenes, but we have a good application of ortho and para-xylenes in the market, and what is used for a major application lies in the production of the PET bottles, which we have been using day in and day out for consuming different kinds of beverages or liquids. So this is where a major application lies, and further in the fiber production as well. Another major chemicals which coming from the petrochemical industry would be the oxo alcohols. So oxo alcohols are basically alcohols coming from the oxo process, and the process is simple. You have this olefins made to react with carbon monoxide in the presence of hydrogen, leading to aldehydes, and further these aldehydes in the presence of hydrogen lead to the production of the oxo alcohols. A major area where the oxo alcohols would be used would be the production of detergents. So with this, we have tried to briefly tell you about the application of hydrogen in the refineries and the petrochemical sector, and hydrogen seems to have a good amount of application with respect to these complexes. Further, we also need to understand in many of these applications, hydrogen is both produced and used locally, and that is why you don't see much of the transportation of hydrogen happening. But this is one area where hydrogen seems to have a good application presently. This might decrease in the future, but still has a great appetite for hydrogen. So with this, we take a break for the current class, and in the next class we will be discussing the application of hydrogen in the chemical industry. Thank you.